How to ensure an A. Not really. Okay, so everybody's gone. Now Sally's here. You came in time. I thought you just got here now, Sally.
No, I didn't. I was here and then she left. Yeah.
Yeah, and then she left.
No, I didn't leave. I just
You just weren't here. That's all. All right. So what we're going to talk about today is more of the Gauss's law stuff and the homework. Thank you, Sally. I hate trying to enforce the rule, but we're trying to be uniform, and it's my job. Okay, so reminder about Gauss's law. By now, you've probably had a fair amount of practice doing Gauss's law. Hopefully, you've done maybe half of the homework problems for the calculus assignment. After today's lecture, everything that you need to know for the assignment we'll have covered. So after today's lecture, you can do everything in the assignment. I know Tori's giving me that goofy look because she told me yesterday, yeah, I haven't even started because I got other things.
I started and then I was like, no, I need to read them all.
Okay, she has other priorities anyway. She'll get there. So just a reminder here, Gauss's law is a fundamental law of electromagnetism that relates the charge to the electric field. Coulomb's law and Gauss's law, it turns out, are fundamentally the same law, just different expressions. And so Gauss's law has two types of expressions. It has an integral form and a differential form. And what we've been working with here is the integral form, as clear by the fact that we have an integral here. But one of your homework problems has the differential form. It's number 5, I believe. So that's the last thing that I need to cover today, so you can do all of the homework problems, is that differential form of Gauss's law. So the integral form says that the flux, which is an integral, is equal to the charge enclosed divided by this constant, the permittivity. So if we can calculate that flux, which in your homework problems, they weren't just the simple cases, were they? Everybody say no. In the homework problems that you've been doing on Expert TA, you've had angles that you had to worry about. But of course, we could calculate those angles, and the problems, I didn't think, were overly hard calculus-wise, but they required a little more work than generally what we're doing in the general physics class, or even what's on the homework assignment, the HWC1, just because you had to worry about angles, and we don't have that in most of what we're doing. So this relationship here, and you know, it really, the kinetic energy calculation that we did, the way you did it is the more straightforward method, Tori, which is probably why it was good that I said I'm going to take the most brutish of force ways to do it. The voltage difference can be calculated from the electric field just by this simple integral. We went over this in class yesterday, except for didn't have the integral sign, and instead I said, if it's a uniform electric field, then we had my equation, I like to say V equals ED, V equals N. And what is this minus sign? Well, that's to tell you that if you move parallel to the electric field, you're going to go to lower voltage, lower electric potential. If you move opposite to the electric field, you go to higher electric potential. We can take this here. Now, this is not Gauss's law, right? That's just standard what voltage means and what electric field means in relating them. We can take that relationship and we can kind of reverse it by using this directional derivative right here. Now, we used that first semester, but still probably most students aren't super comfortable with it. This here, the directional derivative, in Cartesian coordinates, it's easy to write. In other coordinates, it gets more complicated. How many people are comfortable and know what I'm going to write? Okay. What should I use for unit vectors? I hat or X hat? Oh, we have disagreement. The engineers say I, the non-engineer says X. No, yeah. Since you're an engineer, I guess I say that. They spoke louder than you, Tori. I'll write it both ways. I hat d dx plus j hat d dy plus k hat d dz, or for Tori, x hat d dx and for those who just love the arcane, I'll go one step further. There. There's 3 different ways of writing the same thing in a very boring fashion. Now that we're all extremely excited, let's make sure we know what this means. What does the funny shape ddx mean? Because if we don't know what it means, well then, we got some more work to do. No one remembers? It's a partial derivative. It's still an infinitesimal change, Sally. You're right on that. But what it's indicating is that we're doing a partial derivative instead of an exact derivative. What's a partial derivative? What you do with the partial derivative, you say anything that's not the variable on the bottom is going to be treated as a constant. So if I have some function of x, y, and z, and I do the partial with respect to x, I'm going to treat y and z as constants. Now, is that easier or harder than using the... Yeah, it's just way, way easier. So partial derivatives, whenever I see those, I'm really happy because that means it's going to be easier for me to use. So this directional derivative, if I use the directional derivative on the integral, it brings us to the fundamental theorem of calculus. How many people actually remember being taught the fundamental theorem of calculus? Remember being taught it was my question. Okay, so at least half the class remembers that there is a fundamental theorem of calculus. Now the harder question that Tori was getting at, what is this fundamental theorem of calculus?
Is that like derivatives cancel out integrals or something?
Essentially, yes. The fundamental theorem of calculus says that d dx of integral of a dx has to equal a. Right? That's essentially what Michael said. And so we have the same idea here if we put this directional derivative on the integral of the dot product with direction, right? It's dr, so it's derivative. It was an integral with respect to direction, and it was a dot product. It's going to, as Michael said, do you say cancel? Yeah. It's going to cancel. So I can take this del times the integral and say, make that all go away. Now, of course, if you're a purist in calculus, you're going to be kind of aghast at the way I explain that. But I'm a physicist, and we look a lot more at, so what does the math come to? Okay, so if we take this directional derivative acting on the voltage, it gives us the electric field. Now, I have said in class that you can solve most problems using either the voltage or the electric field. And we prefer the voltage for what reason? Don't have to worry about the direction. This here is the connection between the two to help you, like when you need to know what's the direction of force going to be on a charge here, well, you need to know the electric field to know the direction, right? But if we can calculate a function for the voltage, for the electric potential, then at any point we take that directional derivative and it tells us what the electric field and thus what the direction is. So if I have multiple charges and I want to find the electric field at one point, I have to have the function for the components of each of the charges, electric fields, and add those together. With this, I just take the total functions of the voltages for each and add them together. And I take the directional derivative and I get my direction. And in many cases, it's just far, far, far easier. But you have to have this in your toolbox, as we say. You have to have del of V is equal to minus the electric field, or you're not going to be able to get the direction of the force. Okay, as far as new stuff, I believe that's the end of new stuff for today. Did you want to see more on the bottom there, Tori? Okay, I scrolled up in anticipation of going to the next slide. So now, okay, this is new, right? Because we need this for problem 5. The differential form of Gauss's law. Gauss's law, we have that integral form up on top. If we look at the bottom one, you can see that there is some relationship to what we just did. But it's not exactly the same thing. Because the top one, this is an integral over dA, right? Before it was E dot dr. And if I did the del of E dot dr, well, that gave me just the E. Well, here, it's an integral over the surface, so we have a dA. And because it's over the surface, well, you would probably imagine I'm going to have 2 dels to get to having a del left over. But 2 of them will be required because that's area. It's 2 dimensions of space. And so I am not justifying this mathematically other than to say we can see that there is some mechanism where this might come about. Now, what is rho? It's the what? Okay, when we did it before, it was density. A word that we left off on that density was the implied mass density. Just like with mass, we generally don't say, it's the gravitational charge or the mass charge. We just say mass. With the mass density, we usually just say density. In this case, this is still density, but it's the charge density. That is, it's the charge per unit volume. So instead of having the charge enclosed, it's the charge per unit volume that we have here, divided by the same epsilon 0. So let's actually look at problem 5. Has anybody attempted problem 5 yet? Was that a laugh? How humorous that I might have charged. Okay, problem 5 says that you have, and let me read the words here because probably most of you don't have it with you. The average electrostatic field in the Earth's atmosphere, and there should be a possessive there, in fair weather has been found experimentally to be approximately given by electric field is equal to minus E0, E0 being a magnitude, parentheses, A e to the minus alpha z plus b e to the minus beta z, z hat. Now let's start with the simplest of things. What direction is the electric field pointing? Hey, Chad.
Hey. Sorry, I was at the chapel and then I need to go.
What direction is that vector pointing? Not exactly, but close. No, it's parallel to the z-axis. It's in the negative z-axis, negative z direction. And so, traditionally, what direction do we make z? Pointing up. So if it's pointing up, and I think the problem actually specifies this, where, okay, it doesn't specify that z is up. It says z is the height above the locally flat surface. So It is implying Z is up. So if Z is up and it's in the minus Z direction, then the electric field is pointing down. What does that tell you about the Earth's charge? That the Earth's charge must be negative because electric field lines go into negative. So we can look at this, and we already have some interpretive things we can do even without doing any math. Another thing that we can note is what's happening to the strength of the electric field as you approach the Earth, that is, as Z gets closer to 0. Or maybe it's easier for you to say what's happening as Z gets very large. If you go away from the Earth, Z gets very large, and what's happening? What happens to e to the minus alpha Z if Z gets large? It approaches 0. So the electric field approaches 0 if you get far away from the Earth, and it's getting stronger and stronger as you get closer. That's kind of what you would expect if it was a point charge, except if it was a point charge, it wouldn't be an exponential function. If it was a point charge, the electric field would be a 1 over r squared function. Okay, so now we've looked at that. We haven't done a thing to the problem yet. We've just looked at what we can interpret. So now looking at the problem, it says, find the average charge density in the atmosphere as a function of height. What is its sign? So my question is, find the charge density. What's the symbol for the charge density? Rho. Can you see how to find rho? Chad just got here and he's nodding his head yes. Aren't you? Sure? How can I solve this for rho? What's my equation for rho? Not a delta.
Yes, and then electric field, and then times absolute zero.
I tend to forget the permittivity term. I just get into the calculus part and forget. Just got to throw that epsilon 0 there. You can't forget it. Okay, so we have to do this. Directional derivative. What variables is the electric field dependent on? There's only one variable in that function. Not E. Z. Maybe you said Z and I didn't hear right.
No, I thought you were talking about the rho function.
Yeah, the function in blue. It's only dependent on Z, and it's in the Z direction. So we start off by doing del dot E. Now notice I'm doing del dot E, so in the end, when I finish finding del dot E, I have to multiply it by epsilon 0 to get rho. You see why I forget this. So first I'm going to write what del is. Because this is Z hat, I'm going to use x hat d dx plus y hat d dy plus z hat d dz. Dot that with I definitely didn't leave myself enough space. Plan B. Look, plenty of room. Okay, so I'm dotting this. I'm going to put a parenthesis around the entire thing so we don't lose track of the minus sign. When you do the dot product first before the derivative. When you do the dot product, what do you have? Let me change the mode so you don't see all my pen changing. There. Now you won't see my pen changing.
The dot product are also multiplying parallel parts, right?
Yes.
So we only multiply multiplied by the z hat part.
Yep, because this only has a z. When I do the dot product, only the z part is going to turn out. This is 0x hat plus 0y hat minus e0 blah, 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 z hat. So I have 0 multiplied by this, 0. 0 multiplied by that, 0. And I'm left with simply minus e0 dz. Notice the derivative comes before the stuff I'm taking the derivative of. That's kind of an important piece of the process. So that's del dot E. At this point, I'm 2 steps away from the answer, and one of those 2 steps is remembering to multiply by epsilon 0. So I'm going to stop here because you should be able to complete it on your own. I want to make sure that your brain does engage in the process and that you don't simply just go say, hey, let's go look at his notes on Moodle and then write them down. But you see, that process was actually pretty simple. So why do I give you this problem? Because I want you to understand how you can take something like the electric field and using Gauss's law go backward to find how charge is distributed. So yeah, like I said, I'm going to stop there, not finish it. Question to something.
Just do the derivative of that, right?
Yeah, that's all that's left. That and remembering that this is only del dot E, and so I have to put that in here to get. Yeah. Sally.
So x and y are 0 and they don't,
There was no, if I want, I could have put plus 0x hat plus 0y hat here, right? And so when I do the dot product, I had 0x hat dotted with ddx x hat. Well, that was just 0, right? Because the dot product is multiplying the parallel parts together. Now, they could have chosen a much harder problem. You know, you could have had your electric field dependent on x, y, and z and had all 3 components as well, right? That would have made it more complicated. We went with something that, number 1, is a true problem, and number 2 is fairly simple. Any further questions on this? Okay. Next slide. Homework notes. Now, we've already looked at problem 5. The next slide is going to have some notes on problem 5. We probably don't need to talk about that at this point. Problem 2. How many people have completed problem 1? There was at least a kind of answer. And no, it wasn't her. Tori said no. I had hoped everybody would do problem 1 after last week, but
What does it do?
you could have done problem 1 2 weeks ago, right? 2 weeks ago is when we learned how to do problem 1. So it would have been to your benefit to, stay ahead instead of waiting to the last minute. But problem 1 is just using Coulomb's law. That's why we could have done that 2 weeks ago. The rest of the problems, I have told you what to use. Number 1 says Coulomb's law or Gauss's law. You can't solve it with Gauss's law unless you're really, really sophisticated. Coulomb's law is the way to do problem 1. Why is that? How do you differentiate which one you should use?
Does it have simple symmetry?
Yes. You look at the symmetry. Problem 1 was not very good for Gauss's law because it had a semi-infinite wire, a wire that has a starting point but no ending. Because it has that starting point, your symmetry is screwed up at that end. And so that's why Gauss's law isn't going to work very conveniently for problem 1. So Coulomb's law is how to do problem 1. Problem 2 is an electric dipole problem. We haven't studied electric dipoles except for me just talking about, the hydrogen bonds in a hydrogen atom. That's okay. This problem doesn't require you to use electric dipole specific calculations, which are just taking the calculation you're going to do and saying, okay, that's always what it's going to be for an electric dipole. What you do is you find the electric field due to one charge and the electric field due to the other charge. Doesn't sound very hard, right? Of course, you have to add them as vectors. The thing that I have here is for parts 3 in both A and B, it asks you what this becomes as your distance away from the dipole becomes very large compared to the separation of the two charges. And if you are sloppy, you'll just say, oh, the answer is 0. Well, it does approach 0 as you get far away, but the answer that I need for this is an equation. The form of the equation when R is much, much greater than L. So let's think about this. Your equations are going to have something that's like R squared plus L squared. Something like that. If you have R squared plus L squared, if R is about the same size as L, it definitely depends on both of them. But if R is far bigger than L, let's say R is 100 times the value of L. How does R squared compare to L squared? Yeah, 10,000 times larger. And so as R becomes very large compared to L, how do we say R becomes very large compared to L? We just put 2 greater than signs. That means much, much larger. There's not a specific cutoff point. Some people say, oh, 10 is enough because you're 1%. Right? If you're squared, if R is 10 times bigger, then it's R squared is 100 times bigger, and you're 1%. But that just means R is so big that we can ignore L if we have R plus L. If we have R divided by L, that's never going to be the case. But if R is much bigger than L, then we can just say, okay, then L, when I added them together, doesn't matter. If I multiply or divide, it matters. But if we're adding, it doesn't. And so that's what you're going to do to find the functional form if you're very far away. So if you put 0 on that, you won't get credit, okay? I want to make sure everyone's absolutely knowledgeable. Nobody just says, as the denominator approaches infinity, this approaches 0, and puts 0 for the answer. We're looking for a functional difference so we can compare the two cases. Any questions? Who's going to put 0 for those two parts? I'm glad my aim wasn't off that time. That would have been bad if my aim was high, because I threw it a little harder than you would.
I think I would have dodged.
Yeah.
I moved my head faster.
Okay, so there is a heads up for problem 2, just to make sure you don't make that mistake. For problem 3, a lot of people forget to make all of the graphs and sketches they need. You have 3 different graphs you need to make for problem 3. One is plotting the charge density. They give you a function and you just have to plot that function. Right, so you can put that into your favorite plotting thing, right? You don't have to do it by hand, but you need to show that. In fact, I did all of these graphs on Excel because I do everything on Excel. But you need to plot it. And then for part B, you need to plot the electric field for R less than the radius of the sphere. And for part C, plot the electric field for R greater than the radius of the sphere. I combined those and just made one graph that covered the entire range. But make sure that you have all of those plots. And then you have to draw, sketch different things. Don't forget to make your sketches. Right? Because it can be easy to say, well, I made one sketch, forget about the rest. Make sure you have them all there. For problem 5, we've already done that. Like I said, it turns out real easy. I think at this point you can all, hopefully, you can all agree that it turned out to be easy. If that derivative is stressing you out, take a break, because that would clearly be the problem. You need to relax. Problem 6. Problem 6 is an interesting problem. It's a superposition problem. What does it mean to superpose two things? What?
Superpose or superimpose?
Okay, I said superpose intentionally because when I was in graduate school, the teacher said superpose, and I was like, what? It's superimpose. Does he not know the word? Then I looked it up, and either word is appropriate. But when we say superposition, we never say superimposition. And so that's why we start sliding into saying superpose, because it is a correct word, and superposition is based on superpose. So superpose, superimpose, they mean the same thing, so what does that mean we're going to do?
Overlay.
Yeah, we overlay them. Since electric field is a vector, we just add the vectors. Right? That's all it means when it says use superposition. We're just adding the vectors up. But this problem, problem 6, if you don't understand the picture, it'll still be W. So what we have is two solid spheres. One like, nyeh, and one like, yeah. But they overlap. And that region of overlap is what we're interested in. So that region of overlap, where's white? There it is. One has a positive charge density, the other one has a negative charge density. And this region of overlap, there's no charge. And so it's asking us to find what the electric field is in this region. Now let's take some guesses. I'm not going to tell you the answer right now, but let's entertain some guesses. So let's suppose that you put the positive one on the left and the negative one on the right. I'm doing my best to erase everything here. And I have to do it this way, well, because I have the different layers with different things. So this one here is a positive charge. This one here is a negative charge. Charge is distributed. These are insulators, so the charge is just distributed throughout there. What direction should electric field point for a positive charge? Out of it. What direction should electric field point for a negative charge? Into it. So on the one symmetry that we can identify here clearly, we should have on the center line the electric field go like that. Because it should go out of the positive and into the negative. And then you're going to find what it's doing elsewhere. The answer is deceptively simple. The work is not deceptive nor simple. The work is annoyingly drawn out. So how do you do this? If you look at step 1, step 1 says you first need to find the electric field due to each sphere. Define your origin and the Gaussian surface you will use for each sphere. Now, the origin and Gaussian surface are not one and the same. What if, okay, I say for each sphere, you're doing each sphere as if it's the only thing in the world. So for the red one, what shape would you want for your Gaussian surface?
Sphere.
A sphere. And where's the center of that sphere going to be? The center of the charge sphere. Now these are insulating, so you're going to have charge, more charge the bigger the sphere gets. So you're going to find the electric field changes with radius. What about the blue sphere? What should you have for your Gaussian surface there? Sphere. And where should it be centered? Center of that one. Okay, so we have that straight. Simple enough. What should you use for your coordinate systems? Well, there are two ways of doing this. One way of doing this is to say Well, I'm going to put one coordinate system at the center of that one coordinate system at the other, but then I have two different coordinate systems that I have to combine. I find it personally easier to make my coordinate system so that the origin is halfway between the centers of the two spheres. And then when I define my sphere, my x, y, and z coordinates are not just x, y, and z, but they're offset because of where my origin is. But then I can add the components together in an easier fashion. You'll need to break your components up into x, y, and z coordinates. And then you'll need to add the x components, add the y components, add the z components. Now when I do my solution, when you see my solution, you'll see that I did it for everywhere. I'm not sure why really. All you need to do is for the area of overlap. And it's much easier if you just do that part. So only if you feel like doing overkill do you need to worry about other parts. If you just do the region of overlap, right, the reason it's different is because your electric field outside of the sphere is different function than your electric field inside the sphere. So I had region inside this one and outside of the other, region outside of both. I had all these different regions. So that problem it's a lot of adding components. You break them into components, add the components. It's just tedious. And like I said, the outcome turns out to be really simple. So when you get to the end, if you don't have a simple outcome, look to see if you can simplify what you have. If you cannot, then you must have done it wrong. What do you do if you get to that point? You realize, well, this can't be it because this is not simple, and he said it's going to be simple. It's like 5 characters in your answer. If it's not like 5 characters, I don't know what the true number is. Don't say, oh, mine's 4, it must be wrong, or oh, mine's 6, it must be wrong. But what do you do if you don't have that simple answer in the end?
Troubleshoot. I assume not erase everything and start over.
Yeah, don't erase everything, start over. That would be bad. What'd you say? That would be bad, yes. Throwing it away is not to your benefit. After you figure it out, you may want to rewrite the whole thing, but don't throw away your work midway through because you might have been all right except for that minus sign. I mean, that happens so many times because there's so many plus and minus signs where you can make that mistake. I had a quantum physics class in graduate school, and the teacher made the final exam, what for a graduate level quantum class is super simple. And so everybody got every problem right except for a few people made a sign error here and there. I was the only one that made no sign errors, hence I was the only one that got 100% on the test. And I was the only one that got A in the class. That's not the way, by the way, to run a class. The professor had not been granted tenure. He was out of there. He was just, let's get this through. Make it easy to grade. Anyway, what I was going to suggest is if you get stuck in a problem, now you want to give each problem an honest try. Don't say, well, I looked at it for 5 minutes and nothing came to me. Give each problem an honest try. But if you're stuck in a problem, that's where you use your lifelines. Call a friend. Call Chad, Jaron, Tori, whatever. Whoever's a friend of yours. Or me. Come see me in my office. I love to work out these problems. I feel so good when I work out these problems. So, seek resources. Don't just cry or bang your head against the wall or whatever is your way of dealing with frustration.
Don't waste a lifeline calling me because I'll be doing that. Trying to do that.
Okay, that was funny, but... All right. So that was my advice for the problems. All of these problems you should be able to do now. And they turn out to not be super difficult. I actually set up a problem here which is related to number 4. So once again, I'm not doing number 4 per se. At least I don't think I am. Yeah, no, I'm not doing number 4. Just had to make sure. But it's something relevant to number 4. So number 4 is coaxial cylinders. If we read problem number 4, notice I printed these out so I wouldn't forget them. I really hope I gave you guys the right one and not the one with the answers, right?
I didn't see it.
Okay, good. Because I was looking, where I have my files, and I have one that's the answers and one that's not. But they both just say homework C1. Probably need titles that make it so I can tell which one has answers without opening them. Okay, so the problem says two infinitely long coaxial cylinders have radii A and B with B greater than A. The region between them is filled with charge whose volume density in cylindrical coordinates is blah. Okay, so right from there, we're going to find electric field. Which method sounds like the best method to use to find the electric field? Yeah, an answer for coulombs? Any other answers?
Gauss?
Gauss? Good, we got both answers now. How would we determine which of those two to use? Symmetry. Well, what did I say that was relevant to symmetry? That's right. To have symmetry, we use Gauss's law. But what did I say about in this problem that would relate to symmetry? Infinitely long and cylindrical. Huh. That might have a cylindrical symmetry? Yeah, it seems appropriate. So because it has the cylindrical symmetry, that says, oh, this is going to be a lot easier with Gauss's law. If I didn't have simple symmetry, then I'd say, it's probably going to have to do it with Coulomb's law. So the problem is essentially the opposite of this problem. This problem has two cylinders. The problem that we're given is actually a cylindrical shell, is what they've defined. So I'm going to not do this problem. I'm going to look at problem 4.
Don't back out now.
Okay, so I'm going to do problem 4 instead. Now let's look at the instructions so I can follow through carefully. It says that we have, and once again I shall be tricky. Here's the center. I say once again, you guys didn't see me being all tricky. I forgot who saw me being all tricky, but I was tricky. Oh, I have to go down to 2 for this. Actually, no. You guys can't see all the little things I'm doing here, right? Can't see how tricky I'm being. Okay, so that's as close as I can make it to 2, because that's Richard's manual dexterity that makes those not perfect. So this is our situation, and we have, actually, inner radius of A and outer radius of B. Notice I put the B so it crosses over so we realize it's that entire line that's B. And then it tells us that we have a charge density. Yeah, that's right. A charge density that is rho equals A e to the minus CR in cylindrical coordinates. Now, how many people are real comfortable with cylindrical coordinates? How many people have a passing interest in cylindrical coordinates or passing knowledge? All right. We are on a roll, baby. Well, this is in cylindrical coordinates, so this R is the radius like it would be in a circle. Oftentimes with cylindrical coordinates you use rho for the radius. That's fine, rho is just R in Greek. But then we would have something really confusing. Charge density is dependent on charge density? Right, so the R is the radius part in the cylindrical coordinates. Problem is asking us to find, first draw a sketch of the cylinders and the three regions in which you'll find the electric field. So here I've drawn a sketch of the cylinders. This is a top view, so I'm going to label it top view. Side view would just look like a rectangle, right? So there's a top view. What are the three regions which will have different functions for the electric field? The what? There are three regions here that are going to have different functions for the electric field. Okay, the blue, the white, and what? Okay, well, okay. The white inside, the white outside, and the blue. So I'm just going to give these Roman numerals. So I'll have region 1. Region 2, does that show up? Reasonably well. And region 3. So I have my three regions that will have distinctly different answers. Now it tells me I also need to show, the next part. Part B, for each region, sketch the Gaussian surface you plan to use. 3 separate sketches. So I have to take this and say, okay, region 1. Unfortunately, it's not really convenient to take my picture that's on multiple layers. I can't really copy it. That's a drawback. Okay, so I'm now going to just do things with simple circles. So region 1, I have, there's my simple circles. Region 1's in the center. What should I use for my Gaussian surface for region 1? Okay, cylinder, because it's cylindrical symmetry, a cylinder. What more can you tell me about that cylinder? Should be what? Not the size of. It needs to be with a radius smaller than A. And so I'll write in words here a description. Right, I wrote there the words so you can read it and understand, those were the design parameters here. Those are what my restrictions were. It needed to be cylindrical. Why did it have to be cylindrical? I'm using Gauss's law and it needs to match the symmetry. Right, because I had cylindrical symmetry, it needs to be cylindrical so it matched the symmetry. Now if we look at the cylinder, that's a side view, or that's a top view. Let's go ahead now and look at a side view. So if we look at a side view, remember what I say the side view looks like? Yeah, rectangles. So, my side view is like close enough. So that's what my side view looks like. And what is my Gaussian surface going to look like in this side view? I think she said it right. It looks something like this. It's still centered on it. And if we look at this, we have, here's my R that's less than the radius. Here's my height. Can't see the height on the other one, right? So there I have the top view and the side view. Now I need to apply, okay, our time is up. If you want to leave now, leave. Right. I'm going to go through and apply Gauss's law to this part only and not do the rest of it, but I'm going to apply Gauss's law here. So if I'm going to apply Gauss's law, I need to start, of course, with Gauss's law. The flux is equal to the charge enclosed divided by epsilon 0. How much charge is enclosed in this picture? How much charge is enclosed by that red rectangle, well, the red cylinder?
Is there supposed to be a point charge in the center of all this?
No, the only charge is blue in this picture, and that charge has the function right there.
So none.
Okay, so this function here is for A less than or equal to R less than or equal to B, that function. So in this case, the charge enclosed is 0. Well, this pretty much tells me everything I need to know for part A, but I'm going to go through and finish part A, even though I know it's going to turn out saying electric field is 0. When I do the flux, how many surfaces do I have on my cylinder? I have 3 surfaces. So my flux is equal to the flux of the top plus the flux of the sides plus the flux of the bottom. I break it up into 3 separate integrals. Now when I calculate the flux, I have to look at the directions as well as the magnitudes. So what is the direction for the electric field if it exists in something that has cylindrical symmetry? Okay, it has to be going out radially. It can't be going up or down, right? Because if it was going up or down, then you would break the symmetry. So I have to have my electric field lines, if they exist, have to be, going like this, in or out. And of course, the values can change as I go from one place to another, but just to illustrate that. So here the electric fields have to be going in or out. I'm drawing them out as my default negative signs would be in. So my electric fields go like that. What direction is the area on the top? On the top of my cylinder, what direction is the area for the surface? It's always normal to the surface. So on this tabletop, what direction is normal to the surface? Straight up, coming out. Right, so there are 2 directions that are normal, but the one that's out is the one that we use. So that means on top, my area is going like that. On the side, the area is going like that. And on the bottom, the area is going like that. What's the angle between the area and the electric field on the bottom? 9 degrees. So how much is parallel? None. So I'm sorry, I have to go to the next page and my picture won't carry over. Actually, I'll just copy my picture. Just the... Oh, what the heck. Let's do the whole picture.
So why is the field only going in those directions? Why wouldn't it be?
Because of the symmetry, it's restricted. Right, because we have a cylindrical symmetry.
It can only flow along the cylinder?
There we go. Because we have the cylindrical symmetry, it can't matter how you view it as long as you're within that symmetry. So moving up and down cannot change how you view it. If you rotate by 180 degrees from going, from looking this side's up to saying the other side's up, can't change it either because of the symmetry. Right? It looks the same. The charge distribution is the same whether you consider this end up or that end up. And so if the electric field pointed at an angle with respect to that, you'd be able to tell the difference if you considered that end up or that end up. You wouldn't have the same function.
Wait, what?
Okay.
Why isn't it out, is what I'm saying, from the center going out?
Well, it is from the center going out, but it can't, you could not have the electric field doing something like this. Because then if you flipped which side's top and which side's bottom, that would flip over. But our symmetry says the top and bottom, I could define either one as top or either one as bottom, and it'll look the same. But this here wouldn't look the same if I flipped it over.
I mean, like straight up, though, is what I'm saying.
Okay, why can it not be straight up? It cannot be straight up. Sorry, I want to delete that line. It can't be straight up or straight down because the electric field needs to go out of charge or into charge, not parallel to the charge. Right, but straight up or straight down would never go into or out of my charged region.
Yeah, it's definitely.
Oh, okay. I think
Yeah, and also, if it was straight up and you flipped the sides, then it would be straight down, and that would be the opposite instead of the same. Okay, so the flux on the bottom, electric field on the bottom, is perpendicular to the area on the bottom. Therefore, E bottom dot A bottom equals 0. Now there's another easy one. What's the other easy one? The top. I should have said trivial because they're all easy. How does the electric field on the top direction relate to the area on the top direction? I want an answer. They're perpendicular, so once again, if they're perpendicular, then these 3 dots just means therefore. The E top dotted to the A top is equal to 0. So that leaves us our third flux, the flux on the side. How does the electric field on the side relate to the area on the side? They're parallel. So in that case, integral of E side dot dA side. Remember, it is really an integral. It's just because of the directions I didn't worry about the integrals in the first two. That's going to have to equal just the integral of E side dA side. Right? Because of the parallel. So I get rid of the dot product there, parallel parts, just the scalar. But then we go a step further. The electric field can only change as you move in and out. If you move up and down, that's no change because of the symmetry. The electric field can only vary as you move in and out. So because my cylinder, the sides are all a constant radius from the center, what does that tell you about the electric field variation on the surface of my cylinder? It's constant. So we go a step further. E side is constant for constant R. So the flux of the side now becomes the electric field on the side multiplied by the integral of dA of the side. Everyone here knows enough calculus to know integral of dA is A. And so that's equal to the electric field on the side times the area of the side. Well, now we use our geometry. What's the area for the side of the cylinder?
2 pi r times the length of the cylinder.
Yeah, it's the base times the height. If a rectangle, you just cut it, flatten it out. It's a rectangle. The base is the circumference 2 pi r, the height is h. So that's going to be equal to, and now I'm just going to put E, I'm not going to write side anymore because the other two disappeared. E times 2 pi r h. So I have the flux calculation and I have the charge inside. So now I put these together and we have oops, I was thinking about the H and put a C as an H. So my electric field is the charge enclosed over 2 pi epsilon naught RH. Well, for this case, that's 0. I did all of this work because this here is going to be true for regions 2 and 3 as well. For region 2, what will be different? Obviously, you have to draw your new figures for region 2. What will be different in region 2?
The charge enclosed.
You will now have some charge enclosed. How are you going to find how much charge is enclosed?
From the charge equation.
Okay, we have the charge density equation. Now, how do we find the charge enclosed? Charge enclosed is equal to the integral of rho dV.
So can we just say that that equation that's equal to 0 there is the general equation for all the 3 different...
This part that I put in the box, yes.
Yeah. Okay.
That's why I did it once completely. Because we could have just stopped right at the beginning and said, oh, well, E is 0. But I wanted to do it so we have it for everything.
Gotcha.
So for part B, I have to do this integral, charge enclosed, this integral of rho dV over the volume that's enclosed. And so then I rewrote that as rho A dr.
What is it?
What did I do in changing it from rho dV to rho A dr?
You integrated
I'm integrating over what?
the area? What do you mean?
Over cylindrical shells. So that A needs to be the area of a cylinder. Well, as luck would have it, we just calculated the area of a cylinder, didn't we? So that's equal to the integral of 2 pi r h, that's the area, rho dr. Now, for part B, what is my minimum R? There's a technically correct answer and the one you're going to use.
0
Yeah, I'm going from 0 to what?
R.
0 to R, where R is somewhere between A and B in region 2.
I was gonna say, depend on where you...
But, what is the form of my charge density function? What is it from 0 to A? It's 0. Right, my charge density, that function I gave you was only from A to B, and it was 0 everywhere else. So when you do that integral, you're actually going to do integral of 0 from 0 to A, which is 0, okay. And then we do the integral of this, where I put in my function for rho, from A to R. So it will become, let's bring out constants.
How do you decide what R is, though?
I don't.
Okay.
He doesn't seem excited by that answer, but it's the correct one. Oh, criminy. A is the constant in this. I should have changed the constant to B so you wouldn't get it confused with A. I'm going to actually...
A as an area?
This constant here is A. I'm going to call that... Even though the problem calls it A, I'm going to call it B so we don't get it confused with area.
Well, one was lowercase, one was
So this is rho is equal to B e to the minus CR. And so the B here is a constant, so I'm going to bring it out. Integral from A to R. And you'll notice here I have technically a bad math thing. Let's call it RF, and now it's a good math thing. Because you can't have your limit the same as the variable of integration.
IHB.
Okay, these are the 2 pi was constant,
Yeah.
H was constant, and B was constant. So I put all the constant things outside. Just so we have only things that have R in them in the integral. I have to do this integral for part B, and I said I wasn't going to do part B. I'm almost through with it now. How do you do that integral? I can tell you one way. Integration by parts. Integration by parts, one step and you have it. Or you could look it up in the integral table. Either one will work, right? Not going to be picky here. So you have to do that integral, and that tells you what the charge enclosed is for the equation that I have in the box. Now you have to make a statement somewhere that says this equation in the box works for all three regions. Otherwise, it's like, well, what'd you do here? Where'd the magic happen? Right? You have to specify how you got there. And once I go to region 3, what's going to be different from region 2 to region 3? Well, region 3, I'm going to integrate over from A to B because my R final is going to be farther away than B. But the charge ends at B, so your integral goes from A to B. So the charge enclosed is going to be a constant in region 3, but not 0. Okay, y'all feel better about that problem? Not that hard, really. Then you make graphs, and, well, I think you make graphs. Everything makes graphs, right? I mean, it's just fun to make them. Okay. If I think you finish 1,000 words,
Cool.
Yeah, you have some questions at the end. You do have to make some plots, I think, yeah. Plotted as a function of R.